So once again, some diversity there, although some common themes. And I guess one thing that occurred to me is the balance between positive and negative effects. So as we know in cancer therapy, there's a lot of talk at the moment about immunotherapy and stimulating the immune system to help the body fight off cancers. But a lot of the treatments that are traditionally used in cancer therapies actually not only attack the cancer cells, but they attack the immune system. So it seems to be having the opposite effect. So perhaps I'm wondering if you might comment on how your approach is going to actually get that balance right between the positive immune system effects that are fighting the cancer, but at the same time being more selective and killing off the cancer cells.
Yeah, okay. Yeah, so first of all, I'd like to start by my talk about personalised medicines. So the overarching goal of that approach is we can move away from chemotherapies, which damage all healthy cells, and then we can do genetically identify what we have to and redeploy targeted therapies specifically for that genetic lesion. But we're a long way off of that with, as a monotherapy upfront induction, but there is a silver bullet which is called imatinib, and it's other small molecule inhibitors which South Australia's world famous for with Tim Hughes and Deb White, where we have a silver bullet there which is monotherapy and the patients are cured, and now they're actually coming off of the drug after 10 years of treatment and they're still in remission. So that's...
Obviously, I guess to follow on from that, I think, is my microphone on? Yep. We would obviously extensively test with our inhibitors that are quite early stage. We'll always check to see that they're not just killing normal immune cells as part of our pipeline of screening as well. So we want to make sure that we're not adding anything that's going to exacerbate, you know, the issues. I guess, yeah, again, we would initially be putting our inhibitor into a combination with the standard of care, which, you know, carboplatin is going to be one of those standard chemotherapies which you get a lot of the immune system hit. But like I said, the last little bit of data I showed that maybe our inhibitor on its own might be effective. So we really need to test to see if we can just skip some of the other chemotherapies and go straight for something more targeted, like Jason's saying, and hopefully reduce some of those side effects. That would be fantastic.
And perhaps, Eugene, in your work, I mean, again, there's that balance between the protective effect of reducing inflammation, but not knocking out the good things that our immune system does. And how do you see that in your area?
Well, that's a very good point. So often with inflammatory diseases, and cancer is one of these things that has inflammation involved in it. Inflammation is a good thing, okay? We need it. Without inflammation, the general issues that we have would become very big issues. In COPD, the inflammation has gone crazy such that after the smoking has done its work and this trigger of the uncontrolled inflammation attacks the airways, then we have a major problem. Now, in my line of work to mitigate that, azithromycin fortunately just happens to have, as we sort of shown, anti-inflammatory effects. Now, the balance here for me is whether or not you can knock off this bacteria without reducing or ablating the inflammation to a point where it's not able to heal the person's lungs. And lucky, in my research, that doesn't seem to be a major problem. The biggest problem is knocking off the NTHI, which for me seems to be the biggest problem for these people in exacerbations. And the inflammation, well, we have reasonably good therapeutics to handle that. It's just that there's other things going on we don't know about that also need to be knocked on the head.
Okay, thanks. So some of the basic science slides, perhaps from the cancer therapies that you showed us, look to be having an effect, but let's be honest, a lot of them didn't kill all the cancer cells. So when you do an experiment in your dish and you kill 80% of the cells, yeah, is that good enough? Or how do you go from there to actually being something that's really going to knock this thing on the head?
Yeah. Oh, thank you. So I guess, you know, what I'm showing there is a very small snapshot of how obviously we've got a whole suite of ways that we test our drugs to make sure that they are actually hitting their target. And I guess a lot the limitations of using cells in a dish is obviously that it's a very short time frame that they'll survive, and you're trying to simulate what would actually be happening in a person. So obviously these just give us a bit of an indication, and then we have to go through into more preclinical models that give us a better idea, which is where I guess I'm at that point where I'm launching into the clinical models to really nut out what's happening and how effective they are, and potentially, yeah, if we can get rid of all of it, or whether or not we're also not being able to clear all of the cancer. So that's part of our testing for sure.
Sure.
And so maybe I can add to that,
Yeah.
targeting the cancer stem cell. It's like we mentioned in our talks, that's not a very proliferative cell, and it's very refractory to chemotherapies. So it's like, to make an analogy, it's like you have a hive of bees and you kill all the bees except for the queen bee, and the queen bee flies off and colonises another hive. So it's going to come back. So we have to target the stem cell to induce remission and cures.